Brigham Young, who will talk about iron-based Fischer-Tropsch catalysts.
Good afternoon, everybody. I'm going to talk our study on the unit preparation of the well-dispersed iron alumina Fischer-Tropsch catalysis. Basically, I'm going to talk four aspects. First of all, I will introduce the background of our work. Then, I'll talk about the preparation of iron catalyst. The third, we will review the characterization of iron catalyst. Finally, I will end my talk with some conclusions. Fischer-Tropsch synthesis is a very well-known process. There are three main reactions and two main products, paraffins and olefins. The third reaction is a water-gas shift reaction. It is important to regulate the hydrogen and the carbon monoxide ratio so that the reaction will take place. Actually, Fischer-Tropsch synthesis is important today. Still important today because it can produce diesel fuels that are free of the sulfur. That is a common problem for natural fuel sources. The main catalysts for Fischer-Tropsch are iron, cobalt, and ruthenium. Ruthenium is very cost expensive, so the main catalysts are iron and cobalt. This graphic is to compare the iron and cobalt-based catalysts. We can see the iron has a much wider hydrogen to CO relations, so we choose the iron as in our study. Let's focus on iron-based catalysts. There are many advantages of the iron-based catalysts, such as relatively inexpensive, high tolerance for sulfur, very stable when syn gas is a high hydrogen to carbon monoxide ratio, active in the water-gas shift process, and high activity, very selectivity to olefin. Well, the disadvantage is it is very short lifetime. About a couple months, it will lose its activity. The challenge for our work is to prepare a suitable supporting iron catalyst for very bad applications with an greater attrition resistance and a higher dispersion. That's our challenge. Okay, there are three catalysts we prepared. We called 99% iron with alumina oxide additive, and by cold precipitation method, and two 10% iron on alumina support by impregnation method and non-aqueous evaporative deposit method. I will call this sample is 99 iron alumina. This 10% iron alumina water, and this one 10 iron alumina acetone later. Here I want to introduce the preparation procedures of 10% iron alumina acetone. A certain of iron nitrogen put in a flask. This flask was put in a water bath. It's 52 2 degrees C and connected to a pump. After heating and vacuuming about for 12 hours, then add acetal and ethanol solvent, mixture solvent, to release melted iron nitrate. Then put the precalcite alumina. That's just dehydration of the alumina spot. Then shock and evaporation at room temperature, move to the oven to dry at 110 degrees for 12 hours. This is the physical properties of catalysts, of these three catalysts. Mainly the BT surface and the everyday pore diameter after calcination and the reduction. This is the temperature and the time. This slide represents the X-ray integration pattern for three catalysts. The patterns A to C is a calcite sample, and B to F is a reduced sample. We can see the sample C pattern for the 99 iron alumina. They show the alpha iron oxide peaks. And after reduced, this peak is for the iron metal. And the other peaks are for mustite iron oxide, magnetite iron oxide. Sorry. This slide is for the hydrogen TBR patterns of a catalyst. This peak should be to the decomposition of the iron hydroxide, and this peak, is due to the decomposition of iron nitrate. So this peak about 400 degrees C is a reductive peak from alpha iron oxide to mustite iron oxide, and this two peaks is to the mustite iron oxide to the iron, and this peak is for the magnetite iron oxide to the metal iron. Let's turn to the sun reduction, dispersion, and the CO absorption of iron catalysts. This hydrogen uptake for three catalysts. This extender of reduction is the dispersion, is the diameter of iron metal. This CO absorption on iron metals. Let's compare these two samples. We can see the hydrogen uptake for 10 iron alumina acetate is much higher than the 10 iron alumina water. Also, the extent of reduction shows a little bit higher than this sample. Based on this data, we can calculate the dispersion pretty high, about 47.5, and the diameter is 2.6. Okay, this comes to the TM image of 10 iron alumina water sample. This sample is reduced at 500 degrees for 12 hours. This should be the dark parts should be iron, because we can see from the ring images. The same to the 10 iron alumina isotope, the dark part is smaller, the less imaging, and looks very thin. Okay, just the comparison. This for the 99 iron alumina or iron metal, we can see. To further detect the dispersing of iron on alumina support, we use the EDX technique, is energy dispersing X-ray, and to check the dispersing, iron dispersing. This TM picture is a dark field picture. The bright area is for particles, and the dark area is for background. I mean the grids, holes. The right picture is for the energy dispersion. There are 3 curves. This curve, the blue one, is for the iron. 3 obvious peak we can see is just association with these 3 very bright spots. The diameter is about 10 to 20 nanometers. Let's turn to the 10% iron alumina isotope. Let's see. At the first side, we can see the iron curve is very small from this through the red line, very small. And very interesting is alumina curve and the oxygen curve is very similar. I mean the shape is very similar. The more interesting, we can enlarge the iron curve. We found that it's also very similar trend, similar shape. Yeah, that means iron is very uniform on the surface of alumina, on the surface. And because the intensity, I mean the count, is very small. That means because this EDX, there is a resolution about the 2 nanometer, we cannot see a very small one. So that means the particle is very small for the iron metal on this sample. Let's come back to the dark field TM. The displaced line is for the alumina support. Displaced line. You can see this for the iron metal. This is the sample 10 iron alumina water, and the right picture is for the 10 iron alumina isotope. We cannot see very big dark spots. That's very uniform on the surface of alumina and very small particle. This table just a comparison of metallic ion diameter by 3 methods: XRD, hydrogen chemistry, and TM. We get a very consistent result for the later method. This action, the action of the 10 iron alumina isotopes catalyst. Unfortunately, the conversion is not high. I mean, okay. It's very small, about the 35% CO conversion. The other sample for the 10 iron alumina water still running. The CO converting is about 40%. I mean, it's higher than this sample. Okay, these are our conclusions. The iron alumina catalysis obtained by non-aqueous evaporative deposit method has a good iron dispersion, high extent of reduction, high hydrogen absorptive uptake, uniform iron dispersion. And the Fischer-Tropsch reactivity of 10% iron alumina isotope is low. Probably it is due to the metal cluster support interaction and or oxidation. Proposals such as lanthanum oxide are expected to improve the reactivity by reducing the interaction with support. We thanks DOE for the financial support. I also thanks the catalyst group member at BYU for assistance. And thanks for your patience.
We have time for a few questions. Yeah, Jim.
Yeah, I was not, I guess, terribly surprised that at the end when you ran reaction that you didn't get as much activity as you hoped because it was so highly dispersed. I was surprised that you got such good chemisorption, hydrogen chemisorption, and to start it out, you know, with TEM you might have missing some things. You might be having iron rafts or whatever on the surface and not see them as clearly, but the chemisorption values are pretty high. How did the activity of this specially prepared catalyst, the one with the high dispersion, compared to the other 10% iron?
Yeah, it's a little bit lower. Another one, the activities, I mean the CO carbon monoxide conversion is about 40%.
On the other one, okay.
Yeah.
So this one is actually even less active.
Yeah. It's,
okay.
I was surprised.
The other question is, when you were doing the reduction in chemisorption, how much catalyst were you using and how were you reducing it? I mean, you gave some numbers, I think, on but the quantity of catalyst, because obviously these catalysts are so sensitive to water in terms of reoxidation.
For the hydrogen chemisorption, the catalyst we used about 1 gram. But for the TPR, we just use 20 milligrams. Yeah.
Yes.
On your acetone, was the iron particles farther apart with that synthesis compared to the previous pregnation? Iron particles, were they more? You said they had high dispersion of the particles farther apart relative to themselves. Did you notice that with your ethanol acetone experiment?
No, I think the ester and the ethanol's effect just reduce the iron with the alumina surface, so we can get the higher dispersion. Yeah. Is your answer?
This is increased.
I would think we would say it had decreased because you have more uniform spreading of the particles.
Any other questions? If not,